Okay, hello everybody, and welcome back to another session of Chemistry 151. So from our discussion, we have talked a little bit about the history or the historical development that led to our different models for the atom itself, the building block of matter. So as it turns out, our view of the atom has changed quite a bit in terms of historical development. And so today what we're going to do is kind of focus in on the latest model that we find most useful in describing the physical as well as chemical properties and attributes of atoms themselves. Now for the longest time, people looked at atom as something that looks like this, where we are very familiar with the Rutherford model, where we have a nucleus in the center of the atom, where the proton and the neutron reside. And then buzzing around them in some nice orbit are these electrons. We now know, as it turns out, that is an oversimplified way of looking at it. It's actually not a true representation of what the atom really is like. In order for us to kind of really understand what the atom, in terms of its behavior, like, we need to now bring out a brand new way of looking at it. And that particular model is going to be the quantum mechanical model of the atom. And this particular model has one very big fundamental difference between it and the other models that came before it. And it has to do with the way that we describe the electron itself. For the longest time, people thought that the electron was a solid object. Just like for the longest time, people thought that light was a wave-like phenomenon. We now know, of course, that as it turns out, nature has this duality to it, that it can actually hide two different characteristics within the same thing. And so just like a coin where you have a head side and a tail side, if you only look at the head side, you can't see what's on the other end. When you flip it around, then you see the opposite characteristics. In the same way, when you look at light, while it is very apparent sometimes when we experience light that we experience it as a wave-like phenomenon, we also notice that it can have particle-like behavior as well, as basically demonstrated by the photoelectric effect that we discussed earlier. On the other hand, the same thing is going to be true for the electron itself. For the electron, although for the most part people thought of it as a solid object, kind of like a rock or a baseball, for example, we find that when we take a solid object or some sort of particle-like object and bring it down to microscopic level, like to the size of an electron, for example, all of a sudden the wave-like characteristic begin to emerge. You begin to see wave-like properties. And this was actually shown to be the reason why, for example, when you have an electron that are now moving around in a particular orbit, as discussed by Bohr's atom, that they do not lose energy. It has to do with the ability for waves to create standing waves under the correct conditions. And then basically it doesn't lose energy, it then becomes stable. And so the way we're going to look at the atom now in terms of the electrons around them is going to be looking at them as a wave-like phenomenon. So that means that when we look for an electron, there's no way you can actually guarantee that we're going to be able to see the electron in a certain location. So there's no deterministic properties of like a particle. If you think in terms of a particle, if we know where the particle started off, we know how fast it is moving, in what direction it is going, we can actually use simple physics to determine exactly where it's going to be sometime in the future. We can predict its future, so to speak. But that's no longer going to be true for the wave-like characteristics of electrons at all. Once we release an electron from a certain location, even if we know its current speed and its heading direction, so on and so forth, once it leaves, boom, all of a sudden all bets are off. Basically it becomes a wave that's now spread throughout space, and it's only when we detect it next that it basically coalesces and becomes a particle that we can now interact with again. It's a really, really strange concept. But the idea is that for us, we're not going to worry too much about the actual physics of it, the mathematics of it. We're just going to go ahead and use this as a means to understand what the structure of the atom looks like, and then use that to understand its physical as well as chemical properties. And more importantly, this particular model will allow us to explain the makeup of the periodic table, explain why certain things are placed in certain locations, and why certain elements will have similar characteristics, from its neighbors and so on and so forth. So while the periodic table was basically developed much earlier than the quantum mechanical model, this was a very valid proof that this model is very useful, that it is able to predict certain characteristics of the periodic table for us. So let's get down to it and see what it is that we need to know about the quantum mechanical model. We're not going to go through other math, because as it turns out, it's really, really high power math. And even when I was a graduate student and I was actually studying quantum mechanics as a physics major, I found that in that case, the math is just atrocious. It gave me nightmares. So what we want to do is we're going to summarize, kind of like, again, the idea of creating a model that helps us to summarize the essentials of a particular theory so that we can make it beneficial and useful to us. And so here's what I'm going to propose today. So what I'm going to do is I'm going to give you a visual representation of what the atom looks like, okay? And then hopefully using that visual framework, you'll now be able to better understand how it relates to the things that we're going to be talking about in chemistry. And so the model I'm going to give you is something called the atomic condominium. Okay, so the atomic condominium basically has the following premise. We envision that individual atoms are kind of like a big condominium, that there are certain features within that atom itself. And what we really want to do is we want to figure out where the electrons belong in this particular condominium. We're looking at the occupancies of electrons inside of a particular structure, so to speak. So if you look at a very simple situation where let's say look at hydrogen, for example. This is the simplest of all the elements, okay? When we have a single hydrogen atom, we find that if we describe the hydrogen atom as an empty condominium, then we need to then occupy that condominium with a particular electron. And that electron becomes the sole occupant of that particular condominium. It would then have freedom to move about, but the key is where can it move? Okay? What are the possible locations that the electron can find itself in within that condom? That's what we're looking for. It's kind of like asking yourself, well, if my friend lives in a certain location, how do I then find that person? Okay, so let's say you know that your friend lives in a particular condominium. The first thing you have to do is you have to kind of identify the condominium itself. Which condominium does he live in? Okay, in terms of a name, for example. Okay, so once you understand that, that's kind of like identifying the element that you're interested in. The atom of that particular element would then be that specific condo that you're going to be looking for. Once you find the condo, the next step is when you approach the condo, you're going to ask, wow, this condo has a lot of different floors. So on which floor am I going to be looking for my friend? So now you have to limit the location to a specific floor that you might be able to find your friend. So you take the elevator up to that floor, for example. You get out and you look around. Oh, wow, there are multiple units within this floor. So which unit is my friend going to be located in? Okay, so that's the next step, being able to identify now a specific unit to which you can now, hopefully, when you knock on the door, your friend might be in there. And so you now identify a particular unit that he might be in. So now you go up to there, open the door, and gets invited in, for example. And then you're like, oh, wait a minute, within this particular unit, there are now rooms that are also enclosed and with doors. So behind which door, which room is your friend going to be found? So then the next thing you need to know is which room you are going to be looking in. So in other words, to find your friend, you have to kind of find this location that he can be found in. The floor that is on the condominium, the unit within that floor, and then find the room within that unit. And even if you open the door to that unit, there's a possibility that he might have a roommate. So how do you know whether it is your friend or the roommate that you're going to be encountering when you open that door? So all those things are things that we're going to be looking for when we think in terms of trying to locate a particular electron in a particular atom. And because of the wavelength property of the electron, there's no guarantee that we're going to be able to pinpoint it to a certain location. So when we look there, there's no guarantee that we're going to be able to find that. So what we do is that using quantum mechanical model, the mathematics, what it does is that it predicts certain orientations and locations in space, where you have a great chance of finding it. As it turns out, we put a limit of about 90% chance of being able to locate the electron within that particular region. So the whole idea is that how do we then narrow that region of space where we might be able to find our friend, or in this case, an electron, with 90% probability. And that's the whole premise of the quantum mechanical model, and that's the whole premise for the model that I'm going to be giving you. So let's see what that looks like. In general, you can imagine, again, a condominium. That should be fairly straightforward to imagine. If I have a condominium, I find that the condominium that we are familiar with might look something like this. That you have a straight structure that will go up like this. And so as you go from the ground level all the way up to higher and higher floors, you're further and further away from the ground. And so that might be a good start in terms of how far you are from some reference point. Now, of course, in the atom, what would be a good reference point? Well, the nucleus would be a great reference point. So you can imagine the distance from the reference nucleus. As you go further and further away from the nucleus, you can now use that as a reference to locate a particular region of space. And these are then kind of like the floors that we're going to be looking at. The further you are from the radius, so the further you are from the nucleus, the greater the radius. The further you are, the higher up you are, the higher the floor number is going to be. The first thing we need to do is now create this structure of floors inside of our atom. So you can imagine now if I have the nucleus over here, as I go further and further out and create, let's say, hollow spheres that surrounds the nucleus, you find that as I go further and further out, the radius increases more and more. But notice something very interesting. As you go further and further out, notice the amount of space that is enclosed by that particular sphere. When you're very close in, the radius is kind of small, you only enclose a small amount of space. But as you go further and further up, notice the amount of space increases quite dramatically. So it turns out it increases as a cube of your radius over here. And so the further you go, the more room you have, so to speak, to accommodate electrons. And so that's one unique feature about the atomic condo that's a little bit different than the condo that we are familiar with. In our normal view of the condominium, as it goes up, the floor space looks exactly the same. You have the same amount of floor space as you go higher and higher. Not so in the case of the atom itself. So keep that in mind. As you go further and further away, as you go higher and higher in this particular atomic condo, you have more and more space to work with. That means you can now accommodate more and more electrons. So keep that in mind. So the first thing we need to do is we need to somehow create a labeling system that allows us to kind of keep track of all these different things that we have to figure out in terms of the floor, in terms of the unit, the rooms, and then finally the occupants themselves. And so we basically label them using something called the quantum numbers. And to identify the specific location of a particular electron, we're going to be using 4 different quantum numbers. So these 4 quantum numbers, kind of like an addressing system that allows me to now basically, using that addressing system, be able to locate and specifically find my friend that I'm interested in. And so let's see what those things look like. The first of these quantum numbers is called the principal quantum number. This refers to basically a situation where you have what we call main energy levels. The main energy level, sometimes you can hear this being called energy shells. So depending on the book that you use, sometimes they refer to this as energy shells. You can think of this as the actual floors that are now going to be part of our condominium. Basically, in general, the main energy levels basically tells you something about the distance that you are away from the nucleus. So this basically takes into account distance from the nucleus. The farther you are, the higher you are, basically the farther away, the greater the floor numbers and so on and so forth. And to keep track of this, you're going to be using a quantum number. In this first case, you can just use Q with the hashtag. This is actually the number sign. So the quantum number in this case is called the principal quantum number. And it's going to be designated using the symbol N. It tells you basically the floor number, basically. So this would then basically go from 1 to 2, 3, and then so on and so forth. And of course, you can actually go all the way up to infinity. But there's a catch. There's no basically infinite number of distance you can actually go further and further. So interesting enough, when you actually look at the floors in a particular atom, the interesting thing is that as you go higher and higher and higher, the height of the floor begins to get smaller and smaller and smaller. So you can imagine now, let's say for example, you have a condominium that looks like this. You start off with the first floor that has a certain height to the ceiling. Then when you go to the second floor, you notice that the ceiling gets a little bit lower now. Kind of unusual. This is not going to be very practical in our daily situation, but in the case of the atom, this is actually what's happening. As you go to the next floor, the floor gets a little bit lower, and as you go over, the ceiling gets lower still. And so what happens is that the floor gets closer and closer together until they sit right on top of each other. Now, what does that tell us? What this is showing now is it kind of shows us the physical limitations in terms of the confines of the atom. When you reach a certain level where you go beyond that, what happens, of course, in that case is you're now outside of the atom itself. So as the electrons move around between different floors in here, as long as they're within these floors, it's perfectly fine. They're within the atom, part of the atom itself. But if an electron finds itself outside of these floor numbers, out here somewhere, we have now created an ion. We have now taken the electron and basically kicked it out of the atom itself. So, although we say infinity, basically what it means is that there's still a physical boundary as to how far we can go in setting up these floors or principal quantum numbers, the main energy levels. As it turns out, we don't have to go to infinity. There's only a certain number that we need in order for us to accommodate all of the elements that we know on the periodic table. So that's fine. So these are the principal quantum numbers. Think of these as your floor numbers. These are your floor numbers. All right, so once we have the main energy level that now taken our atom and kind of separate them into different floors as we go further and further away from the center. We now need to know what happens on each of those floors. Because when we do reach a certain floor, we find that there is now structures within that floor itself. And so the second thing that we can now look at, okay, are called energy sublevels. Okay, energy sublevels. And sometimes you hear these being referred to as energy subshells. Okay, so when you hear the term subshells being referred to in textbooks, for example, they are really talking about these sublevels, and these are now, okay, our units, okay, in our condominium. So they are the ones that are now basically divvying up the floors themselves. So the floors is now divvied up into units. And in the same way, okay, when we look at these now, okay, they represent basically the different types of units that you can have, okay, different shapes of occupant space, for example. Just like when you go into a particular floor of a particular condominium, you might have different kinds of layouts for the interior of these units. You may have a one-bedroom, room studio, for example. You might have a two-bedroom apartment. You might have a 5-bedroom apartment, and so on and so forth. So these then designate the different kinds of arrangement in the spaces that you can have available within the floors themselves. Okay. So in this case, we have now another quantum number. Okay. In this case, you don't have to worry about the name of the quantum number. Just kind of use the reference that we use to compare what they are. They actually have specific names that are given to them. Okay, so these are usually known as the angular momentum quantum numbers. Again, like I said, don't worry too much about it. Okay, but what we would do is that we would use a label to kind of represent these, and the label is going to be given L. So this is kind of like the address. This is going to make this a little bit darker over here. This is going to be N. Okay. So N tells me what floor I am on. L tells me the kind of unit, okay, that I can have. Okay. So these are the kind of unit that you can have. Okay. And so in this case, okay, you can think of this as, again, the kind of shapes that the unit would take on. So this basically take on shapes of space available, for occupancy. Okay, so what kind of different shapes you can have? And in describing the shape, instead of using all of the just numbers, sometimes it gets a little bit tricky. You can actually use a letter to represent this as well. But basically, what we're going to do is going to tell you what kind of available space you will have based on a particular number that looks like this. It tells you how many different kinds of shapes that are going to be available. And this is going to be starting from 0, 1, 2, up, all the way to n minus 1. Okay? So interesting enough, the number of different shapes of spaces that are available, no, the number of units that are available is dictated by which floor you are on. And that makes sense because as it turns out, when you're close in, you don't have a lot of room, you can have a limited number of units. As you go further and further up, you can have a bigger amount of space to work with. You can now afford to put more units in there. So this shows you what it looks like. Okay? So notice in this case, if I have, on the first floor, when n is equal to just 1, 1 minus 1 gives you 0. So that means the only possible value that I can have for L is just 0. Everything else is not going to be there anymore. I can only have one single unit in my first floor, for example. When I get to the second floor now, the second floor now is going to be 2. 2 minus 1 gives me 1. That means I have to now end this at 1. So 0 and 1, that gives me, there's going to be two different types of units that are available. So we can then associate each of those possible numbers for L with a particular shape that we can now look at. So let's see what that looks like. So in this case, we can actually take a look at when L is equal to 0, when it's 1, let's go ahead and draw this all the way up. So L is equal to 0, 1, 2, 3, 4, and so on and so forth. And we're going to use a specific letter for each of these number representations. So it turns out for L is equal to 0, this is now going to be called the S sublevel. S sublevel. And the shape that it takes on, the S actually basically looks like a sphere. Looks like a sphere. But rather than remember the shape, you can actually remember the S just by thinking of this as a first type of unit, it could be thought of as a studio unit, for example. Okay, so this is now the studio with just a single room for occupants, for example. We get to the second one now, okay, for the L is equal to 1 type of unit, we now have the P units, okay, the P units. And the P units is, this should make a pair, that kind of looks like a figure 8, and as it turns out, we find that there are different orientations that we'll take into account later on. So that means there are other rooms that can now have the same kind of shape and so on and so forth. Again, instead of using a shape to kind of designate the letter, we can now think of these as our prime units, for example. That will have a certain number of rooms that are going to be assigned to it. Okay? So in this case, as it turns out, the prime units will have 3 bedrooms. So these are 3-bedroom apartments, for example. Then when you get to the next one, for n is equal to 2, we now have the designation for D. Okay? And the general shape for this one might look something like this, where you actually have now. Okay. And again, these shapes are shown, okay, it was shown in the textbook as well as in the discussion that we had. And again, the website that tells you the orbitron shape will actually be very useful in visualizing what these shapes look like. But again, rather than trying to use a shape to remember this label, we can now think of these as the deluxe units now, the deluxe units. And these are now basically 5, okay, bedroom apartments, so to speak. Okay. When we get to the next one, these are now the F units. And here I'm not going to even try to attempt to draw the shape of these units, okay? But the idea is that in this case, to remember the F designation, these are now the fabulous units, for example. So studio, prime, deluxe, and fabulous. They'll tell you what these different shape of units are. In other words, there are different kinds of apartments that are available. You have the studio, you have the 3-bedroom, 5-bedroom, 7-bedrooms, and so on and so forth. And the number of bedroom designation will come next when we look at the next quantum number. So far we have 2 quantum numbers that we have used. Okay? So the first one tells us the floor that we're interested in. The second one tells us the particular unit that we're looking for. Okay? Now once we find a unit, what do we do next? We look inside the unit, and the unit will then have sub-structures as well. So let's go ahead and erase this and put the next step on. Later on, we'll go ahead and summarize this for you as well using some examples. So after we have now designated the floors and the units, the main energy levels and the energy sublevels, the next step is now to look at what's going on inside the units themselves. And within the units, we now have what we call orbitals. Orbitals. Orbitals are the actual occupant space for the electron. They're kind of like, again, the rooms that the electrons are going to be sitting in. So when we look into this location, we're going to say that, okay, there's now going to be a 90% chance that we're going to find the electron associated with this particular location in there somewhere. Okay? And in the case of the Bohr atom, for example, this would then be the orbits that will house a particular electron as it goes around the nucleus. Do not, however, confuse this with orbits. They're not the same thing. So orbitals and orbits are not the same thing. Orbits are very predictable. You know exactly where the electron is going to be along that in the path somewhere. This is orbitals, you can't figure it out, so to speak, exactly. There's only a probability of finding the electron in here. And so in this case, for the orbitals, you can think of these now as the rooms that we're going to be assigning a particular occupant to. In this case, there is going to be a quantum number. This is called the magnetic quantum number. Magnetic quantum number. And the magnetic quantum number uses a letter M to designate the number of possible rooms that are going to be in there. And so this is going to depend, as it turns out, on your unit itself. So depending on what L is, there's going to be a certain unit that you're going to be looking in. Then that unit will have a certain number of rooms designated by this number, M sub L. So don't let the symbol throw you, it just tells you the number of things that can be in there. And in general, what you find is that you can start off with the following. We have the value minus L plus 1, for example, all the way to 0 in the middle. And then you can have L minus 1 and L. Now, of course, this looks kind of funky because this is a lot of math. And again, this tells you basically the number of rooms that are going to be available. Number of rooms that are going to be available. So what does that mean? Let's take a look. If L is equal to 1, that means that, I look at the next one, is 1 minus 0. Basically what you have is that you only can have one possible room. And so we're going to see that. Another way to kind of look at it is you can think of a different way. You can think of in terms of the number of rooms available. Okay. Can be found using 2n minus 1 as your count. Okay. So basically, where n is a floor where that type of unit is first appears. Okay. Okay, first appears. So you can use either way of figuring this out, but let's go ahead and keep this in mind, and then when I do the example, you can actually see where this comes in. Okay. This basically just allows us to figure out for each type of unit, whether it's going to be the studio or the prime or the deluxe or the fabulous, we can then figure out how many rooms there should be. So think about this. If I have the S, the studio unit, how many rooms can a studio unit have? Well, the studio units first appeared in the n is equal to 1, the first floor. So when it comes to the first floor, n is going to be 1. Okay, 2 times 1 give you 2 minus 1 give you 1. That means studio can now have only one possible, only one possible unit. Okay, one possible room. In this case, it's going to have a value of 0 at this point. Okay. On the other hand, when you look at now the prime unit, the P units, the prime units first appear on the second floor. Okay, on the second floor. When it comes out on the second floor, you now have 2 times 2 give you 4, minus 1 give you 3 possible rooms that you can have now. And so in that case, it will take on the value of 0, 1, and minus 1 over here. Okay, so that's the thing that you're going to have. Again, don't worry too much about the actual numbers themselves. They're just actually used for just keeping track of housekeeping, so to speak, just bookkeeping, so that you know exactly what value to give a particular electron. For us, we just have to figure out how many there are and where they're going to be in general. So this is probably going to be more useful. But once you figure it out for one of them, then it's going to be true for those units all the time. All right. The next thing that you have, the last type of quantum number that you need is something called the spin quantum number. The spin quantum number has to do with the spin of the electron. So you can actually take a look at this is the spin. So this is now spin quantum number. The spin, in the simplest term, can be thought of as kind of like looking at the gender of the occupant, for example. So for example, the gender could be male or female. So in this case, you think in terms of spin, there's actually 2 different types of spin. Now, physically, what it means is that if we were to imagine, an electron as to be some sort of a spherical object, for example, that spherical object can then spin as it moves from one location to the other. Kind of like the Earth, for example, as it revolves around the sun, it's also spinning on its axis. So depending on whether it's spinning in one direction, we can now designate that spin, or you can have it spin in the opposite direction. So when we look down, we can either see it spinning clockwise or counterclockwise. So there's 2 possible orientations. In the same way, you can kind of imagine again, in terms of the occupant of a particular condominium, you can have either a male or female occupant, 2 possible choices and so on and so forth. So in this case, basically you can think of this as a up or down spin for the electron. So if the electron is spinning, let's say in one direction, we say it's going to be spinning up. If it's spinning in the opposite direction, it's spinning down. Turns out the choices are at this point arbitrary for us. We're not going to worry about what designated is. So when we look at a particular electron, we always assume it to be spinning up to begin with, and then we'll take into the account the other one later. All right, so basically in this case, the spin number is going to be given by a value, a symbol S, and this is going to be either plus or minus 1. Only 2 possible values. Plus 1 is the up spin, minus 1 is the down spin, for example. So what it does is that you can think of this now as kind of like the occupants. The designation of the occupants. 2 possible types of occupants within a particular room, for example. One that's spinning up, the other spinning down. So now with all of these 4 numbers, so to speak, we can now give an address that is going to be unique to each of the electrons. As it turns out, there is a principle called the Pauli exclusion principle, which dictates that in any given atom, no 2 electrons can have the exact same 4 quantum numbers. Okay, one of them has to be different. You know what? They cannot be on the same floor, in the same room, in the same unit, in the same room, and have the same spin. Okay, at least one of them has to be different. So either they are on the same floor, in the same unit, in the same room, but have different spins, or they can have the same spin, but they cannot be in the same room, okay, in the same floor, in the same unit, and so on and so forth. Okay, so that's the idea here. So each of these now is going to be unique to a particular electron in that particular atom, kind of like fingerprints, for example. All right, so how do they put this together and look at what it looks like? So let's go ahead and apply some of these. So unfortunately, I have to kind of erase some of this, but you can actually have it in the notes, so you can refer to that when we do the next part. So let's see what happens now when we actually look at the different floors and see what's going on. So let's take a look at if n is equal to 1. So you know what? This is the first floor. So what's going on the first floor? With n is equal to 1, what we find is that, okay, L will have a value that's going to be equal to 0. Okay, L is going to have a value equal to 0. That means that there's only going to be what? One type of, room. It's only basically the studio unit, so to speak. So you're going to have now the S unit in here. And within the S unit, you can think of this as now the studio unit. Okay. And in this case, ML is equal to 0. There's only now one room. Okay. So, in this single one, the first floor, you have a single S studio in there. That studio has a single room, available for occupants. Okay. But here's the interesting thing. This is now just the framework of the condominium. It doesn't have any occupants yet. So the last part, the occupant will come with the spin that we're going to put in later on. Okay. So basically, what happens is that when you look at building an atom, you think of creating this framework around the nucleus of the atom, and then you ask yourself, well, where do I put in all the electrons that are necessary now to balance out the protons in the nucleus, such that I can now have a neutral atom, so that everybody is now sitting in their proper places, so to speak, in order for me to have this coherent atom that will be that can be discussed. So that's the first one. Let's take a look at now the second floor and see what happens. On the second floor, that means in this case now, n is equal to 2. Okay? So the first floor, n is equal to 1, second floor, n is equal to 2. So once we have n is equal to 2, we can now ask ourselves, well, how many rooms are there? Now, L in this case, if you recall, it's going to be what? Okay? In this case, n is now 2, so it's going to be n 2 minus 1, giving me 1. So that means the highest level you can go to is 1. That means you can still have the 0 and the 1 that are possible. So then L has the possible value of 0 and 1. Remember, it goes from 0 to a maximum. So you can think of this as the maximum L value you can have. So from 0, 1, 2, 3, all the way to n minus 1. So here's 2 minus 1, giving me 1 as my n of my series of numbers. That means I can have 0 and 1 as two possibilities. That means I now have the S studio, and I now have the P available to me. So here's my studio. This is now my prime unit that I've just introduced on the second floor. So the prime unit actually makes its appearance on the second floor. There's no prime unit in the first floor. Okay? So studio on the first floor, second unit now has studio and the prime unit at the same time. ML now is equal to, this is because you can go all the way up to L is equal to 1, you now have minus 1, 0, and positive 1 as all possible values for the ML. That means you now have 3 rooms available in the prime. Plus, you have 1 room from your studio. So altogether, you now have 4 rooms on the second floor that's available. Okay? So the first floor, you have only 1 room available. The second floor, you now have 4 rooms available. Makes sense because now you're farther away, you have more space to work with. Okay? So that's the second floor. So let's see what happens when you get to the third floor. Okay? The third floor, again, in this case, if you don't understand all the details here, don't worry about it. Just understand the fact that you have different types of units on the different floors, and then figure out the number of rooms that you now have in total on that particular floor. That will give you the number of electrons you can house there. Okay? Now you have n is equal to 3. Now you're on the third floor. That means L now maximum you can have is going to be equal to 3 minus 1 equals to 2. So that means that L can now have value of 0, okay, 1, and 2. Okay? We now have 3 different kinds of units available. So then, of course, the O is the S unit available. Then you have 1 being the P unit, and 2 now are the D units. These are now your deluxe units. Okay? The deluxe units. The question is how many, okay, do I have here? In this case, when you find the number of rooms, you then now have possible minus 2 on this side, minus 1, 0, plus 1, plus 2. 1, 2, 3, 4, 5 possible rooms that are available in your deluxe unit. So this is 5 rooms. But of course, you also have a P unit which had 3 rooms, and then your S unit which has 1 room. So altogether, okay, 9 rooms available. Okay. Interesting enough, these rooms are all available within the atom itself, even without any electrons. So if you look at the hydrogen atom, if you have the hydrogen atom and you don't have the electron yet, you just have the hydrogen nucleus, then imagine around that hydrogen nucleus you have all these features that are already available, okay? And when you place an electron in there, the electron would then be placed into any of these locations possible. Now, of course, the ideal situation is what happens when you place the electron in the lowest level. So in general, when you start putting these electrons in, you want to build the electron up in occupancy from the bottom on up. The lowest position, and then you slowly work your way further and further away from the nucleus itself. Okay? When the electrons are in the lowest position possible, we call that the ground state of the atom itself. When the electron gets basically somehow interacted with the environment and somehow absorbs energy so it can hop up to a higher level, it has gained energy, we say that there will be an excited state, without leaving the condom, of course. If it leaves it, then it becomes an ion at that point. Okay? So the excited state is kind of like a situation where if you have a hydrogen atom that has all these different floors and rooms available that are empty at this point, you put one single electron in there to create that hydrogen atom. The electron, if it sits down in the 1s studio, then it is not at the ground state. It has the lowest energy. But as you begin to bring that electron to a higher location, somehow if it absorbs a photon, for example, it makes a quantum transition to the second floor, to 2s, for example. Now there's nothing in 1s, now you have a single electron in 2s. We now call that an excited level. We are now given energy and make the atom a little bit more energetic. Of course, it's not going to stay there for very long. So what happens, of course, that the electron can now drop back down to the low level, and in doing so, it becomes ground state again, and then give out the extra energy in the form of a photon, for example. And so the idea of the photoelectric effect in terms of the atoms absorbing and releasing energy in the form of light, they are actually absorbing and releasing energy in quantized value, called photons, as predicted by basically Einstein. All right, so you can actually do the same for the 4th floor, and 5th floor, and so on and so forth if you like. But for us, we're going to go ahead and stop here for now, and see then how we would actually go about relating what we have just learned to the periodic table. Oh, maybe I should have just left this here, but that's all right. So let's see what happens. Well, as it turns out, if you look at the structure of the floors and units and rooms and so on, and occupants and so on and so forth, you can now see that when you look at the periodic table, it clearly outlines and defines where the electrons are, so to speak, in relation to the arrangement of the elements in the table itself. And so as it turns out, if you look at the periodic table, there are a certain number of rows that are the periods of your periodic table. As it turns out, those period numbers correspond to n, the principal quantum number. So this is kind of like the first period is really like the first floor of your atom. The second period is the second floor, third period is third floor. Those are now your main energy levels. As you get further and further down the periodic table, you're now getting further and further away from the nucleus of your atom itself. Also notice something very interesting. Notice that on the first floor, you can only accommodate 2 electrons. In other words, you can only be used those 2 electrons to build 2 different kinds of atoms. So in the first one, when you have the hydrogen, for example, you're now putting an electron in the 1s orbital. Occupying an electron in that one location give you now the hydrogen atom. And so its place is right here at the beginning of your periodic table. When you put the second electron in there, okay, obviously in this case, when you put the first electron in, you have to put it in as a spin-up electron. When you put the second electron in there, it now has to be a spin-down electron, so that they can both, occupy the same room, okay, without conflicting, okay, and without violating Pauli's exclusion principle. So in that case, notice in this case, we put helium all the way over here. As it turns out, that's a little bit of a digression from the pattern. The reason for that is that helium really should be sitting right over here. But it is placed there because of its chemical property similarities to the rest of its neighbors underneath it. And we'll come to that in just a little bit. Okay? But you can actually imagine that this would really belong sitting right here next to hydrogen, where you now have the single 1s orbital completely filled in on the first floor. Okay? Once you have that, if you're going to go ahead and build the next atom, where you now have 3 electrons to contend with, guess what? You can no longer fit an electron on the first floor. You must now go to the next floor of occupancy, and you now basically put 1 electron in the second floor in the first unit, which is the S unit. Okay? And so I did that. So even within the same floor, for example, different units that we have, S, P, D, F, and so on and so forth, they all will have slightly different energy. Although they're in the same floor, they're not the same height, so to speak. So that the studio is actually a little bit lower energy, and then your prime level P is a little bit higher, D is a little bit higher, F a little bit higher still within the same floor. And so the idea is that when you do fill this, there's an order to filling them. You fill them S first, and P, and so on and so forth. Okay, there are, of course, going to be a little bit of exceptions that we'll deal with a little bit later on. But that's the idea. So as we continue to put electrons in there, we find that after we finish filling up the S, all of a sudden we now fill out things over here. These are now basically the prime units, the P sublevels. And you can kind of tell that they are because you can see the amount of occupancy that you have. Notice in the S, this can only be 2 occupants, right? 1 room, 2 roommates. And so notice that there's 2 columns here, and these 2 red columns represent now the filling of the S orbitals, the studio orbitals, so to speak. When you get to over here, notice you can have 1, 2, 3, 4, 5, 6 electrons that can now sit in this particular unit. Or 6, that means you have 3 rooms with 2 roommates each. This gives you now the P orbitals that are now being filled in, when we start occupying the conduit with the electrons, and building the various elements there. And we'll actually have a way of kind of keeping track of that in just a little bit when we talk about electron configuration. But then notice what happens in the middle here. As you look in the middle over here, this is now the filling of the deluxe unit, the D orbitals. And you can kind of tell because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 available spaces in there, so to speak, spots. So that means if you have 2 occupants per room, there's now 5 rooms here, 2 occupants each for a total of 10 electrons that you can now fit in there, while filling up these particular orbitals in here. And then finally, of course, down here, the Fs, you find that Fs can actually have now 14 occupants. The Fs, as it turns out, first appears on the 4th floor. So 4 times 2 gives you 8, minus 1 gives you 7. And then 2 times for each electron give you 14. Now in this case, there's a little bit of odd shape over here. This is to show that this thing over here is actually belongs right in this section. So you can imagine taking the periodic table, slicing it down right here, and then pushing them apart, and then sliding this up as a connecting bridge. This is actually where all these elements belong in terms of the number that you find. So that's the reason for this. It's just that it's kind of cumbersome. It's going to stretch it too far. This is a little bit more compact and a little bit more efficient. Also notice something interesting. You would think that as you go across that everything on the same floor should be on the same level, but they're not necessarily true. So notice here 1 goes all the way across, so these are the 2 that are on 1, that's fine. And then for 2, going all the way across, you have now S and P. So for the second one, you can actually accommodate 8 electrons on the second floor. That seems to be fine. But then what happens on the 3rd floor? On the 3rd floor, we find that we can accommodate what? 9 rooms, 18 electrons. But if I go from here to here, there's only what? 8 electrons. So where's the other 10? As it turns out, the 3rd level D unit actually gets pushed down 1 level. That's because, again, the idea is as you go further and further, all of a sudden the level in terms of energy kind of overlaps and crosses over. And so as it turns out in this case, when you get to this point, the 4s energy level is actually a little bit lower than the 3d energy level, at that particular level. So you fill these items in first before you fill that in here. And again, don't worry about the reason for that at this point. We're just going to show you how we can predict that's going to happen there. And so really, these are the n numbers, so 1, 2, 3, 4, 5, 6, 7. So these are the 7 floors. And then when you look at the middle block here, this one really belongs to the what? The 3rd floor. This is now the 4th floor, 5th floor, 6th floor. Everything gets shoved down one floor, so to speak. They are up one floor. And then, of course, same thing over here. The F gets pushed down even more. It gets pushed 2 down on the periodic table. So this really belongs to the 4th floor. This is the 5th floor, and so on and so forth. And again, this has to do with the height of these different units crossing each other. So a good way to do this is actually look at the electron configurations on the website Web Elements. If you go to Web Elements, for example, you click on any element, hydrogen would be really good. When you click on the element, hydrogen, and then you go to the upper right corner, and then you look at the other physical properties, and you click on that, and you look at electronic configuration or electron configurations. They will then show you a map of these different levels that are then laid out. In your textbook, there's also a good picture there as well, so I won't reproduce it for you here. But suffice it to say that there is an order in which you will then fill the electrons in, okay? And so how do we then represent the filling? How do we represent the electrons that are inside of a particular atom? We do so by using something called the electronic configuration, or electron configuration. The electron configuration basically tells us, a little about the addressing of the electrons. How do we address them so that we know what floor they're in and what unit they're in? And so if you only need to know what floor they're in and what unit they're in, you know where the unit now occupies a particular family, for example. That's all we need to know, that they're within that family. Then we can use something very simple. The way we do that is we go ahead and use the floor number. So this is now the principal quantum number. And then next to it, we're going to be using the symbol for the units. So this is now the sub-level. And then we're going to put up here a number. We call that X. And so this is now designating the number of electrons that you're going to be looking at that is sitting in this particular location. So these two, first two symbol designates the address. It tells us exactly which unit we're now looking in. So this is now, of course, the principal quantum number. You can think of this as the floor. This is now the actual unit. And then you tell us how many electrons are in that unit. So we can now use that to designate each of these particular elements, telling us where the electrons are found within this atomic combo. So for example, if we look at hydrogen, hydrogen has basically one electron that we have to worry about. So where do we put that one electron? We will put that one electron in the 1st floor S unit, and there's going to be one electron sitting in there. So this is now the electron configuration for hydrogen, where we tell you, there's one electron is sitting right there in the 1s orbital, 1st floor S unit. That's it. When we go to now helium, helium has 2 electrons that we have to worry about. And so in this case, we say that, we're going to put both of those electrons in the 1s orbital because we can accommodate it. So we can put 2 electrons into this studio unit on the 1st floor, and then this will be happy. So this is now the electronic configuration for helium. When we get to the 3rd one now, let's say look at lithium. Lithium would then have 3 electrons that we have to accommodate. So the idea is that when we add up all the electron number up here, it should give me the total number of electrons that I have here. So in this case, I can now start off again. I will first put 2 electrons in the 1s orbital, but then when I do that, I've now completely filled in that 1st floor. I can no longer put any additional electron in there. But as it turns out, I need one more. So where do I put it? I put it in the next floor. And the next one now comes in 2s. And I'm going to put 1 electron in there. And so when you add it up, 2 plus 1 is 3. I give you back a 3 electron that is associated with your lithium. And so on and so forth. And in the same way, if I look at now further down, let's go ahead and look at carbon, for example. Carbon will have 6 electrons. 6 electrons. So where do I put these electrons? Well, I can put 2 in the 1s orbital. I can then put 2 in the 2nd floor, studio. But then that only accounts for 4 electrons. Where do I put the extra 2? The other 2 now must go to the next available occupant space, which is now going to be your 2p, and that will take care of 2 electrons in here as well. So you give you a total of 2, 4, 6 electrons, taking care of all 6 of the electrons. So the question is this: how do I know which comes next? Which is the order of the orbitals that I have to fulfill? As it turns out, basically in the textbook, they show you a very nice visual way of keeping track of which one to go next. And so I'll reproduce it up here really quick. You start off basically with 1s, then you go to 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f. Okay. The next one, of course, is G. So it turns out once we get to F, we don't actually need any more. So we can actually stop at F. And then 6s, 6p, 6d, 6f, 7s, 7p, 7d, 7f, and so on. So you can imagine going on. It's kind of like a little triangle shape. Okay? And the idea is that you will follow this according to a particular path that you go. So you start off up here, drawing an arrow going through here. So you go to 1s first. So go ahead, fill in all the 1s first. Okay? Once you are done filling in the 1s, you then go and fill the 2s. Okay? And those over here, after I go finish 1s, I go to 2s. And then you continue with this pattern of arrows as you come down, okay, this triangle. So it tells you go from 1s, you go to 2s next. Here, follow this to the next one, 2s, and from here you go to 2p. And then notice in this case, after 2p, okay, you go to what? 3s. Okay, and from there up 3p, but instead of going to 3d, you continue to 4s first, and then you double back to go to 3d, 4p, 5s before you double back to go to 4d, 5p, 6s, and then double back to 4f, 5d, 6p, 7s, and so on and so forth. Okay? So this allows you to kind of keep track of where these levels are now kind of intermingling and shifting relative to each other. You don't even have to worry about that, just keep this in mind, and that shows you pretty nicely. Another way to do it is just going to look at the periodic table, which kind of shows you how to do it, right? Here's 1s, here's 2s going across to 2p, here's 3s going across to 3p, and from here, notice that you talk to what? 4s first before you get to what? 3d right in here, and then you go back to 4p, and then now 5s, 4d, and then 5, and so on and so forth. So if you match this with this, it matches up very nicely. It can tell you where you need to go. Okay? So let's do one that's a little bit more interesting. Okay? So what if now I have to do one that is, okay, in here somewhere. Let's take a look at iron, for example. So iron is 26. So if I go ahead and look at iron, okay, has 26 electrons. So how do I keep track of all of them? Well, if I go ahead and do this over here, it tells me, okay, I go from 1s, there's going to be 2 in there, 2s, I can put 2 in there, I can then go to 2p, which I can put 6 in there, okay? So in this case, I've done this now up to here, and so far I have, 10 electrons, I still need some more, so I continue. After 2p, where do I go? I go to 3s, and so you have to recognize that whenever you have an s orbital, you can only accommodate a maximum of 2 electrons, okay? So that's 3s there, from there I go to 3p, and p can accommodate 6 electrons. So after 3p, you now go to 4s, and that can accommodate 2. So here's another 10 electrons. Oh, okay, I'm getting close. I got 20 so far. So I need one more location where I can now put 6 of them. So after 4s, where do I go? And I'll go to 3d. And in this case, although d can accommodate 10, I don't need 10. I only need to accommodate 6 more. So I put this as 3d6. Okay? So when I add it all together, you get back your 26 electrons, and they have now been housed very nicely in this particular iron condom. Okay? So notice if you kind of trace it here, you can actually see it here as well. Okay? So 1s, okay, 2s, 2p, 3s, okay, 3p, 4s, and then 3d right here. And then 1, 2, 3, 4, 5, 6. There it is. Okay, 6. Right there. Now, of course, sometimes it can get pretty silly. By the time you get to go, for example, number 79, okay, gee, do I have to do this for 70 and count 79? That's going to be pretty tough. So there's a way that you can actually do a shorthand notation, so to speak, okay, that you can actually simplify the method itself, simplify the actual representation. So how do we do that? Well, let's take a look. Imagine now if I compare, let's say, for example, okay, neon, okay, with, let's say, sodium. Neon basically has 10 electrons. Sodium has 11 electrons. Okay? So let's see what they look like. So neon would be 1s2, 2s2, 2p6. Ah, there we go. 6, 7, 8, 9, 10. I'm done. Okay? So this is now neon. Then you get to sodium. 1s2, 2s2, 2p6, completely filling my p already. But I need one more. I need one more. So where do I put it? I put it in 3s1. There it is. Okay. So when you compare the electron configuration for neon and sodium, you notice something very interesting. They look almost the same, except for this last piece right over here. So if you look at the things as before, okay, from here to here, they are exactly the same. So that means then, instead of always starting from the beginning and then working my way in until I get to this end here, what if I say, well, you know what? What if I start off at some sort of stepping stone? What if I start off at a location that I already know the electron configuration for? I can then use that as a starting point and then go from there. That makes it easier, right? You have some sort of in-between point. And that's what we're going to be looking for. In this case, the stepping stones that we're going to be using are going to be the noble gases. They will always be used now as a reference starting point. They can allow us now to take a shortcut, so to speak, to get to my final destination without having to go from the beginning all the way through. So I can now replace all of this here with the fact that this is really just neon's electron configuration. And the way I'm going to do it, then we'll go ahead and write down neon, okay, and then put it in square brackets like this. This just means that start off with the electron configuration of neon, and then from there, okay, figure out where I need to go for the next one. So where is neon? Well, neon's right over here. So from here, where do I go next? The next is now going to here, 3s. I put one electron in. I now have sodium. So basically all I need is add 3s1 to that, and they will then give me the complete, okay, for sodium. So this is much nicer, much easier to figure out. So that means for any given element that you want to find the electron configuration for, okay, to find this compact shorthand notation, look for its nearest previous noble gas neighbor. Okay, nearest previous. So for iron 26 here, its nearest previous noble gas neighbor would then be what? Argon right over here. Okay, so the other way that I could have written iron, okay, would be, if here's iron right here, its nearest neighbor is argon, you can then put argon over here, Ar, and then from there, where do I go next? Okay, argon just finished up the what? 3p, so after 3p, you go to now 4s. Now this is 4s, and you then put 2 electrons in the 4s, and you don't have enough yet because argon has 18, you only have 20 so far. The next step, of course, is now to put 6 more in the 3d6. Okay, so altogether you now have 26 to give you the number of electrons for iron. So this is now a much more compact way of writing the configuration for iron than the long drawn out way that we had before. And this becomes even more apparent when you get to the really large atoms with lots of electrons. Okay. Just to make sure you understand, let's do one more. Let's try gold, for example. Okay, let's see what happens when we do gold. Let's try, let's make something even more challenging. Let's go ahead and do uranium. So uranium has 92 electrons. 92 electrons. Okay? So where do I start? Again, obviously I'm going to start with 1s. I'm going to go ahead and look for the closest, noble gas neighbor of 92, which is now right here, 86, radon. Okay? So if we start off with radon, that has already 86 electrons, that's a pretty good starting point. I don't need a whole lot more to get to 92. So if you look at this, this was of course 6p. So I basically just ended 6p. So up here, I just ended 6p. So the next thing I need to go to now, I go to 7s. So from 6p to 7s, you can kind of see from 6p to 7s, which is right over here. So I can go ahead and go 7s, put 2 in there. That still only gave me 88, not quite there yet, okay? So after 7s, where should I need to go? Well, as it turns out, I need to go back now to 5f. That's where this is now, 5f right here, and put in the number of electrons that I need there. So I'll go to 5f. The question is, how many do I need? Well, let's take a look. I have 86 here, plus 2, I have 88 total. I need to get to 92. I need to have 4 more, okay? 4 more. So then this is now your electron configuration for uranium. Much nicer than if you start at one end, go all the way to a long winding road all the way to the end. Okay, that's the idea. All right, so this is a very simple way of, again, addressing the electrons that are in a particular atom, telling you exactly where the electrons are going to be distributed within this condo structure of the atom itself, telling you where these locations are. Okay. One thing that's kind of limiting, of course, is that you only know to the unit that these guys are in. You don't know which room they're in, and also you don't know their orientation in terms of are they spinning up or are they spinning down? You know, what kind of occupant are you going to be looking at? And so as it turns out, okay, there's going to be another tool that we can use. Okay, instead of using just the electron configuration, if we need more detail, we can then go to one more, which is going to then be, okay, what we call electron, okay, block diagrams. Okay. So in this case, in the textbook, if I recall, they call it block diagrams. So depending on the, okay. Yeah, sometimes I guess some people call it orbital diagrams as well. So block or orbital, depending on, again, how you want to draw this up. It's slightly different depending on the textbook that you use. Okay. Basically, in this case now, as the name would suggest, whether it's electron orbital diagrams or block diagrams, you're not going to be looking at more detail. You're locating to where the actual orbitals are going to be that a particular electron is going to be finding itself. So how would this look compared to what we saw earlier? So let's take a look at the hydrogen over here. Again, remember hydrogen has the electron configuration 1s1. That's pretty nice, okay? And if I look at lithium, okay, this have a 1s2, 2s1, 3 electrons, okay? So if I look at carbon, this will be, okay, 1s2, 2s2, 2p2, okay? Let's do one more. Let's do, okay, oxygen. Okay, it will be 1s2, 2s2, 2p4, okay, for 8 total, okay, for oxygen. So this tells us where the electrons are up to the unit that they're found in, but they don't go any further. So in the case of a block diagram, we will now actually draw out the specific orbitals that they're in, the specific room they're in as well. So this is how we will do it. We're going to go ahead and label this as 1s, and then we're going to either draw a little block in here, or in the book they use a little underline. That's fine, either way is fine. I like the block, it looks kind of cool. And then over here, we're going to tell you that we're going to have one electron sitting in this 1s orbital block. So we're going to use that, and we'll automatically use the up arrow as my first occupant. The first occupant goes in there, one single occupant. This is now the electronic orbital diagram, or block diagram for hydrogen. So 1s1 here is one F the block, one arrow pointing up, one electron sitting in there. Okay? This one's own. So this I have 1s. Okay, I can do this again. Okay, so I have 2 electrons in there, one up, now one down. So when you put the second one in the same orbital, make sure you orient it down. And the question is, how do I then represent the 2s here? Well, it's the same thing. So 2s now looks like this. Also, the single electron in the upper here. So you draw each of the orbitals separately. Okay, so here's the second unit right over here. When I get to here now, it gets a little bit more interesting. 1s, 2s, they still look the same. Both of them fold. 1, 2, 3, 4. Okay. Now I have to take care of 2 electrons that are now in the p unit. In this case, the p unit will have 3 orbitals. When you go ahead and write down 2p, you have to now draw each of them separately. So now I have to have 3 blocks, each block representing one of the orbital or rooms. Then I will go ahead and assign the electrons into these rooms. And here's the thing. When you assign electrons, they always want to be at minimum energy. You know what? They want to interact as least as possible. So the idea is kind of like, when you go to their coffee shop, if you buy a cup of coffee, you're going to sit down on the table. If a stranger is sitting at a table, you're not going to go join them if there are basically open tables available, especially nowadays, right? So you're going to go ahead and sit at your own table until absolutely necessary. Do not pair up with somebody on a particular table. In the same way, if I were to put 1 electron into the first room, when I need to put 1 more in, I'm not going to put that in here because then they're going to repel each other, not going to be comfortable. I want to give them the space to begin with. So In this case, I would actually put a second electron also in the upward orientation in a separate room. If I need to go to the next one, let's say nitrogen, I would then put a third electron in a third room also spinning up, okay, to represent, okay, having them separated and giving them breathing room, so to speak. Okay? So that's how you would represent that. What happens when you get to here now? So in this case now, you have 1s, 2s, 2p, okay? And again, the first two are completely filled. How do you fill the last one? Well, in this case, again, you need to have 4 electrons, so you use the same rule. So you go 1, 2, 3, and then you go back and you double up. Now you go ahead and put that 4th one in there, okay? So by the time you go to fluorine, you would then put 1 more in here, and by the time you get to neon, you put 1 in here. So neon would then have a situation where all the rooms are now completely occupied. All right, so that kind of covers the idea of electron configuration and electron block diagram or orbital diagram, and these are basically just ways to address where the electrons are found within the atomic condo to tell you what the internal structure of the atoms look like in terms of where the electrons are. It is important to know where these electrons are, especially the outermost electrons, where they're lying and in which room they're in, so to speak, because as it turns out, that's the key to the understanding how atoms interact with each other. Because as it turns out, because the electrons are on the outside, they will be the first to interact between atoms, and they will then be the determining factor as to what can happen during chemical reactions. Okay? So for now, okay, I'm going to go ahead and stop here, and then the next time we come back, we're going to look at more details in terms of how to interpret the periodic table based on this particular way of looking at a electron configuration around it. Okay? Right, until next time, take care, stay safe, and see you then.